Hello everyone, welcome back to Bytes of CC. So in this lecture, we'll be learning about the binary heap. So this lecture, I'll show you the properties of binary heap and I'll discuss how to create, insert and delete from the binary heap. And also I'll be discussing some questions, some selected questions from the competitive exams. So now binary heap is extremely useful to implement priority queues, and there is also an important sorting called heap sort, which arranges the values in ascending or descending order. So I will be dealing with priority queues and sorting in some other lecture, and it is also used in Huffman encoding for data compressing and also in real-time systems, especially the embedded systems. And this is also used to balance the load in the server when web requests come in, so that no one server is overloaded. So now let's see what a binary heap is like. So let's discuss the important properties for a binary tree to be a binary heap. So first of all, it has to be a complete binary tree. Now, a complete binary tree is something that looks like this, where all the levels except for the last level is completely full. So as you can see, this level, that is a root level, it has got exactly two nodes, and also this left child has two children, and also the right child has two children. So this is how a complete binary tree looks like. Whereas if your tree looks like, say mm, this, and a node over here, this is not a complete binary tree. And now we come to the second property, second most important property of the binary heap is either the value in the parent node will be less than equal to the value of the children, in which case it will be called a mean heap, or the value of each parent node will be greater than equals to the value of the children, which is known as the max heap. Now as you can see here, when you come to the mean heap, this the root node has the value 9, which is lesser than both the children 12 and 18. 12 has a value which is less than both 15 and 14, and 18 has a value which is less than 72 and 31. And finally, 15, the child of 15 has a value of 21, which is of course greater than 15. So, and in this case, as you can see here, so 70 is greater than both 35 and 42. 35 is greater than 21 and 18, and 15 is or 21 is greater than 15, and here in this case 42 is greater than both 16 and 30. So as you can go through this, you have understood that the minimum, in case of the mean heap, the minimum element will be found at the root, and in case of the max heap, the maximum element will be present at the root node. And this also calls for a corollary, which you can assume that in case of a mean heap, the maximum element will be present in one of the leaf nodes. Like in this case, 72 is the maximum element in this case, in this particular tree, and 72 is a leaf node. And when it comes to max heap, the minimum element will be present as one of the leaf nodes. So in this case, the minimum element for this particular tree is 15, and 15 is a leaf node over here. So when we talk about the operations, the different operations like creation, insertion, deletion, so there is a generic kind of, it's a two-step process where a new node is added to the tree, or we generally pop the root element, and I'll explain that later. So that is the first step, and the second step will be to actually rearrange the nodes to ensure that the binary heap property, that is the property 2 of binary heap, that is the max property or the mean property, mean heap property, is maintained. So if you can't make out what is going on, I'll be explaining it in more detailed step in the next slides. So this second step is known as the heapify operation, where we rearrange the nodes to make sure that the mean heap or the max heap property is maintained. And in case of an insertion, we rearrange the node from leaf to the root, or we can call it a bubble up operation. And in case of a delete operation, we actually rearrange the node from top to down fashion, and you can also call it a bubble down operation. So in this particular lecture, I will be using the array implementation of binary heap. Now, binary heap can be implemented as a Fibonacci heap or a leftist heap, but array implementation is the most popular, the most uncomplicated version. And in most of the in most of the applications, binary heap is implemented as an array because it's simple. So what happens here is, for any node which is at index I, the left child of the node will be present at index twice I plus 1, and the right child will be present at index twice I plus 2. And this is when your indexing, the array indexing, starts from 0. Now, if your array indexing starts from 1, which is, we generally do not start indexing from 1, but anyways, if it starts from 1, so in that case, your left child will be present at this -1, and this right child will be present at this -1, which is left child will be present at index twice I, and the right child will be present at index twice I plus 1. And your root element, the root of the tree, will always be at index 0. So now if we try to represent this particular tree as an array, this particular binary heap rather, as an array, it will look something like this. So 9 is a root element. So 9 will be present at this position, that is at the 0th position. 9 has two children, 12 and 18. 12 is the left child. So 12 will be present at index number 2 into 0 plus 1, that is index number 1. So here is where the left child will be present, and the right child, that is 18, will be present at index number 2 into 0 plus 2, that is index number 2. So this is where 18 will be found. And now we move on to index number 1, or this left child of this binary heap, that is 12. So 12 has two children, 15 and 14, and index of 12 is 1. So index of 15 will be 2 into 1 plus 1, that is 3, and index of 14 will be 2 into 1 plus 2, that is 4. Now we move on to 18, which has the index value of 2. So the left child, that is 72, will have the value 2 into 2 plus 1, that is index number 5, and this will have the value 2 into 2 plus 2, that is index number 6. And now we move on to this particular node, 15, which has index number 3, and this is the left child. Therefore the index of the value containing the node containing the value 21 will be 2 into 3 plus 1, that is 7. So therefore now if we represent this particular implementation, this particular binary heap as the array implementation, the array will look like, so I have already written 18. So index number 3 is 15. Where am I? Okay. Index number 3 is 15. This is going to be your 14. This is going to be 72. This is going to be 31. And this is going to be 21. So this is how the array representation is implemented, and this is very important. So I would ask you to take a screenshot of this particular slide. And now we move over to insertion. Why I am choosing insertion? Because that will give you an idea of how this heapify operation takes place. So now suppose you have a new node, say 8, which is to be added to this particular binary heap. Now as you can see, this is the mean heap. So the value of the parent will always be less than equals to the value of its children. So now the first thing is that whenever we add a new node to a binary heap, this will be added as a leaf node. Now which leaf node? Now we will scan the last level, that is the leaf level, from left to right, and we will find the first empty position. Now this is the last level. So the first position is of that of the child of node 15, that is the left child of node 15 rather. Now this is an occupied position. Now we check that if 15, the right child position of 15 is empty, and we find that yes, this is empty, so we add the new node 8 to this. Now the problem what arises here is 18 when we add 8 to this node, the mean heap property gets disturbed, because now 15 has a value which is greater than its child. So what is the obvious step? We just have to swap the value of 15 and 8. So now 8 comes over here and 15 is added as a 15 comes to the position as that of 8. Now since there has been an exchange, we will also have to make sure that the new node value does not contradict the mean heap property of its immediate parent. Now its immediate parent is 12, and in this case it does violate the property. So there will be another exchange between 8 and 12, and now the tree looks like this. Now, say for example, this contained a value less than 8, say it contained a value of 6, and there had been no exchange. Like it just didn't need to exchange, we didn't need to exchange 6 and 8, right? So this comparison operation would have stopped right here. But since there is an exchange, we will further have to compare 8 to the value of its immediate parent. So this comparison will actually stop at the root node if the interchange does not stop in the middle. So we will need to compare 8 and 9, and here of course we will have the final exchange, and this is the final binary heap. So the interesting part is that when you are entering a new node, you do not have to compare with a whole bunch of nodes. You will always have to compare with the parent. So this is a very time efficient operation, because in case of the worst case complexity, like you have to, like in this case we had to exchange the node till the root node. In case of worst time complexity, there will be the worst runtime complexity will be O log n if you have n number of nodes in the binary heap. So you're not comparing with the sibling nodes, you just will compare with the immediate parent, and the heap property is maintained. So if there are a whole bunch of nodes, this is a very time efficient operation. Now if you're just thinking that why is it O log n, I have made a detailed discussion of why this kind of operation takes log n time in my BFS lecture, so I would just request you to go through that. So this is how the insertion operation happens in a binary heap. And in case of a max heap, if it had been a max heap instead of a mean heap, it would have been just the comparison thing would have been just the opposite. Like in this case we are comparing if 15 is less than equals to 8, but in case of a max heap, we would have, the comparison would have been like if 15 is greater than equals to 8. This is the only difference. Other than that, everything is the same. Now we will move on to how to create a heap. So in this case, since we have shown the insertion on a mean heap, I have selected max heap for the create operation. So you will be given a whole set of elements, a whole set of values, and you will be asked to create a heap, a mean heap or a max heap out of that. So you can just you take the order and you can just imagine that they are present in an array, and I will actually use this array implementation in order to show you how this bunch of elements in this array gets converted to a max heap in this case. So there are 10 elements in this array, and I have started the indexing from 0. So you can start it from 1, but this is how the convention is like. So I've started from 0, and this is the algorithm of the create heap creation operation. So we will go line by line and we will understand and we will implement that in this particular example. So it says that we start from here, build max heap operation. So we will first initialize the size of the heap, which is equals to the length of the array. Size of the heap is how many number of nodes are present in your binary tree or binary heap. So obviously that would be the length of the array. And now we will start building the heap from the middle element. Now this is what this line tries to convey. So we start a for loop, and the for loop, it will be a decremental for loop. Okay, so the for loop starts from floor length array divided by 2 minus 1 to 0. So now what this particular thing means, and why did we need this floor? So we need this floor because, say, instead of an even number, your heap contains, or your array contains an odd number of elements. Say your array instead of 10 contains 11 elements. So length array divided by 2 will be 11 by 2 will be 5.5, right? And when we take a floor operation on this 5.5, what we do is simply we just delete everything that's beyond decimal and we return the value 5. And now this 1 needs to be subtracted from this number. So 5 minus 1, which is equivalent to 4. Now since my indexing starts from 0, I had to subtract 1 from this value, because technically, so my pointer is now at this position, that is 4, and index number 4 means the 5th element in your array. So if you start your indexing from 1, you do not have to do this decrement operation. Like, you do not have to you can just use floor length array divided by 2. So this is where our heapify operation starts from. So now we will call the max heapify operation, which, and we pass on this array, the total array, and this index number, which is 4. So let's come to this max heapify operation. So we compute the index for the left child, and in this case, since again I am using the indexing from 0, it will be twice into index plus 1. So twice into index plus 1, in this case twice into 4 plus 1 would be 9, and the right index would be, the right child's index would be 2 into 4 plus 2, that is 10. Now we declare a temporary variable largest, and the value of the largest is set to the index number which is passed. So in this case it will be 4. Now we come to this if loop or if checking, which will check that if the value of the left index is less than the size of the array, and if the value contained in that position is greater than the value contained at the original index position which is passed, that is the value of its parent more appropriately, then we will assign the value assign the index number left to the temporary variable largest. So what it means is, so now you will simply compare the value 25 to 24, and if you find that the value 25, that is at this position 25, is greater than the value at this position, you will assign the value of assign the value of 9 to the largest. So now your largest has a value 9. Now when you come to this if checking, since the right child does not exist in this context or in this array, so this evaluates to false in this case, and of course we are not doing anything what is inside. And now we do the final checking, where if the largest contains the value which is not equals to the index, which means initially your largest was this and now your largest contains the value 9. So that means that this value is larger than this value. So naturally you will need to interchange 24 and 25. And this is what your array looks like now. This is 25 and this is 24. 24 comes here. And next we will call a max heapify on this particular index. Now this will be true in other cases, but in this case, since this is a last node, there is no left child or right child to this particular node, so this max heapify operation will practically be nothing. It will just return nothing. It is so the control goes back to this build max heap, this particular block of the algorithm, and now there will be an decrement of the I value, and now the value of the I will be 3. So we come to this particular node, that is index number 3, 9. So 9, now I am not going like line by line. So 9 has two children, that is 49 and 18, which is found out in this max heapify operation. Now what happens here is the largest gets the value of 3 initially. Now we first compare 9 with the leftmost child, that is 49, and now largest is assigned the value of 7. Now in this case, in the previous case the right child didn't exist, but in this case the right child does exist. So now we will again have to compare between the right child and the largest element found so far. So in this case 49 and 18, and this evaluates to false. This particular thing, the a right greater than a largest, this evaluates to false. So the value of largest is still 7. And now what happens is, at this particular case, since the largest and the index are different, there will be a interchange operation. So 9 gets interchanged with 49, and 9 comes here and 49 comes here. Now we will see that if 9 potentially has any children, so the index number of 9 is 7, and the left child and right child of 9 would have been in this case 15 and 16. So these are not present in this particular array, so 9 does not have a child. So we move the control to here, and now we move to this particular node, that is at index position 2. This is where your current I is. Now index position 2, or this particular node, has two children, that is 83 and 35. And moving in the same way, we will first compare 5 to 83, and now the value of the largest is set to 5, and we will compare 83 and 35, and the value of largest still is retained at 5. And now we will see that since this value is greater since this value is greater than this value, there will be an interchange operation, and this is what the array will look like. So 83 comes here and 5 is shifted down at index position 5. Now again, the children of 5 will be present at indices for index number 5. It will be present at 11 and 12, which is not present in this array, so we ignore. And now the control comes over index number 1, that is 17. So now 17 has two children, which is 49 and 25. Now 17, so using the comparison, 49 is the largest of the three. So naturally there will be an exchange between 49 and 17, and this is what the array is going to look like. Now 17 is shifted to index number 0, 1, 2, 3. So 3 has two children, which will be present at index number 7 and 8. So that is 9 and 18. So now here is where the max CP5 operation will once more take place. So there will be in the same way a comparison between 17, 9 and 18, and 18 is going to be the largest element. So this particular loop is going to evaluate to true, and therefore the largest will be set at index number 8, and there will be an exchange between 17 and 18. So 18 is shifted at the position 3 and 17 is moved down at position 8, and this is what your array is going to look like. So now there will be no further max CP5 operation possible on this particular arrangement. Now we move over to the first element, that is 12. Now 12 has two children, 49 and 83, and when we compare, we find that 83 gets the largest value. This is the largest value, so the largest index is this, and therefore 83 and 12 are exchanged, and this is what it looks like for now. And now 83 is shifted at position number 2, and 2 again a max CP5 potential max CP5 is going to take place. So the children will be present at these two positions, that is 5 and 35, and it is found that 12 is less has a value lesser than 35, so there will be a comparison, there will be an exchange between 35 and 12, and 12 shifts down to this position, that is I think position number 0, 1, 2, 3, 4, 5, 6, at position number 6, and 35 is moved up to this position, and this is going to be your final heap. Now let's see how it looks like. So this was the final index position. Now 83, this is going to be your root node, and this has two children, 49 and 35. This is left and this is right. And then 49 has two children, the left will be 18 and the right will be 25, and 35 has two children where the left child is 5 and the right child will be 12. And then we have 18, the child of 18 will be 9, the left child is 9, right child is 17, and then we have 25, and 25 has one left child which is 24. So this is how your max heap is going to look like, and you can just take a screenshot and you can always check that if there are any violation. So in this case, the value of the parent will be greater than equals to the value of both its children. So now let's see how the delete operation happens. So in case of the max heap or the mean heap, we have got this data structure just to make sure that we always find the minimum or the maximum element at the root. So we are potentially trying to extract the minimum or the maximum of a set of elements. So the deletion will always happen from the root, the max, that there is the extract minimum or the extract maximum element will always happen from the root node. And what happens here is, this is the first index position, that is the 0th or the first index position, and what we do in case of delete is we interchange the value at the first position with the value at the last position, that is the last index position, which is this. So in this case 25 and 12 will be exchanged. 12 is a leaf node. Now it becomes a root, and we just delete this. That is, we pop the last element in this array, and now in this in this, what shall I say, yes, it's an array and it's also a tree. So now what happens is, this binary heap looks like this, and there is of course a violation, because as you can see, this is also a max heap, and since 12 goes to the root, which is less than both its children, so there has to be a rearrangement operation. So a rearrangement, in this particular rearrangement operation, this has to be compared to both its children, like 14 and 16, and the maximum of its children will be shifted to the parent position, and that will be, this will come down to the child position. So in this case 12 comes down over here and 16 is moved up. And since there are there is one more level. So now you will compare what is the value contained in the level immediately below, and since in this case the immediately below the value contained here is 8, so there is no violation since it's a max heap, so the operation stops over here. So this is how the deletion operation happens in the binary heap. Now let's go through some of the questions in the binary heap. So you will have three types of patterns as I have observed. That is, one will be a direct application of the heap properties, and there will be some questions of heap properties and some common sense, and then there's a third kind where it will be based on heap properties, some common sense, and it might contain need some other theory also. But generally it is based on the binary tree what shall I say, properties. You will just have to remember all the binary tree properties that you have learned so far while you are answering the heap questions, especially these kind of questions, and sometimes these questions. So this particular question came on GATE CSE to 2024 on set 1, and it says that there is an array. So this is the array and this is heapified. So which one of the following options represents the first 3 elements in a heapified array? So the first thing is that it didn't mention if it is a max heap or a mean heap. So now in this particular case, you will actually have to go through the options in order to find out, or in order to guess what might be the heap structure, like if it is a max heap or a mean heap. So as you can see here, this is the maximum element in your heap and this is the minimum element. So among these options, you can find either this 131 or 11. So clearly these are not the options. 82 is neither the smallest or the largest element. So your answer lies somewhere between C and D. Now this particular question, as I would say, is a very easy question, because first of all, this is a max heap. So the second largest element of this particular heap is 111. And since the second largest element, in case of a max heap, the second largest element will always be the child of the largest element in order for the heap property to maintain. Similarly, in case of a mean heap, the second smallest element will always be one of the children of the root element of the tree. So in this case, for the first three nodes means the root node and its two children. So since 131 is your root node, so 111 must be in the options. So in this particular case, this was a very lucky thing that this contained only just this option 3 contained this value 111. So you can right away say that this is the right option. So in this case, though there is an array, you really do not have to heapify the array. You just have to use some common sense. So you can right away find out which is going to be your right option. If both contained 111 instead of 11 as is given here, then of course you had to create the binary heap, and then you had to find out that what would be the third node. In this case, there was no need. So the next question is, which one of the following sequences when stored in an array at locations A1 to A10 forms a max heap? So in this case, your indexing starts from 1 and it ends at 10. So there are 10 elements in your array. So let's just number them: 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So this is also a direct application of heap property, where you will just have to track the parent and the children node, and you will have to see, and since this is a max heap, you will have to ensure that the value of the parent is greater than equals to value of both its children. So if there is a contradiction, then that is not a right option. So this is also, you will just have to go through the options and just find out which one does not have any kind of violation. So let's get started. So 23 has the children 17 and 10. So both are less than 23. So it's okay. So now let's move on to this particular node. 17 has children 6 and 13. So there is no violation. 10 has children 14 and 1. No violation. 6 has children 5 and 7. And there is a violation. So definitely this is not a max heap. Now let's move on to this particular case. 23, 17 and 14. Fine. 17 is compared to 7 and 13. Again fine. 14 is compared to 10 and 1. Fine again. 7 is compared to 5 and 6. So far so good. And then 13 is compared to 12, and this is the max heap. So I leave it as a homework to you to find out that if these two contain a contradiction. You just go through this particular case. And if you find anything wrong, just let me know. I'm moving over to the next question. So it says that there is a binary max heap and the elements are stored like this. So this came in ISRO and also in GATE. So I found this question both in CSE GATE paper and also in ISRO. I don't remember the year. I think 21 or 22. I don't remember actually. So anyways, so there are elements. This is a max heap as we can see it here, and there are elements stored in the array, and there has been two delete operations. So this was exactly, if you remember, this is exactly the example I used to show you how the deletion operation takes place. So after 25 was deleted, your array looked like this, and now you will have to again so this will be a good recapitulation also. So you will exchange the first node with the last node, which is this part. So 16 is exchanged with 8. So 16 comes here, 8 goes here, so 8 goes here, and 16 gets deleted, so forget about this node. Now 8 is to be compared to 14 and 12, and since this is a max heap, so 14 comes over here and 8 is shifted at this position. Now 8 is to be compared to 13 and 10, and the largest among the three will be shifted to this parent position. So 13 now gets shifted at this position and 8 comes down at this position. So your array will look like 14, 13, 12, 8 and 10. So 14, 13, okay, 14, 13, 12, 8 and 10. So this is your option. So in this case, so for questions like this, you don't actually go through the options right away. Try to do it, and of course your option, like your answer, will match one of the options. This is also a very direct application of the heap property. So now comes heap plus binary tree property question. This came in GATE 2020, GATE CAC 2020. So the array representation of a binary heap, mean heap contains 1023 elements. The minimum number of comparisons required to find the maximum in the heap. So be very careful what is required or what is being asked. So this is a mean heap and you have to find the maximum of the heap. So if you remember, I said that in case of a mean heap, the maximum of the lot will be present as one of the leaf node, and in case of a max heap, the minimum of the lot will be present as a leaf node. Now since this is a complete binary tree, so complete binary tree has a property like if there are n nodes in a complete binary tree, so there will be n by 2, the floor of n by 2 internal nodes. So the number of internal nodes will be the floor of n by 2, and the number of leaf nodes will be ceiling of n by 2. So the ceiling of n by 2 means, again taking the 5.5, or suppose you have something like 2.1, and if you are to find the ceiling of 2.1, it will return the value 3. So if you have anything beyond the decimal for this particular whole number, the ceiling will the value of the ceiling will be this plus 1, and you will just ignore the trailing decimal whatever. So both floor and ceiling, they actually try to return or they actually not try, they actually return an integer. So in this case, since you're trying to find the maximum, so the maximum element will be present in one of the leaf nodes. So the number of leaf nodes will be the ceiling of 1023 by 2. So 1023 by 2 is actually 5, 1, 1.5, and now if you have the if you take a ceiling function of it, this will be 5, 1, 2. Now suppose there are 4 elements A, B, C, D, and you are to compare which is the largest of the 4. So suppose you have to compare element wise. So A will be compared to B, and say you find that A is the larger of the two. So now A will be compared to C, and now say you find out that C is the larger of A and larger between A and B, A and C. Now C will be compared to D, and finally we'll find out which is the largest. Now what I meant to say is there were 4 elements and the number of comparisons to make was 3. That is the minimum number of comparisons that you had to make to find out which is the largest among these 4 were 3. So you can generalize this as when there are n elements, the number of comparisons to find the minimum or maximum of those n elements will be n minus 1. So in this case, our n is 512. So the minimum number of comparisons which is to be made, actually the number of comparisons we can say, it will be 512 minus 1, which is 511. Now we move on to the next question, which came in GATE 2024 for set 1. So this is also similar. So it says that there is a binary mean heap. It contains 105 distinct elements. Let k be the index of the maximum element stored in the heap. The number of possible values of k is. So this is literally the same as the last. So they are asking you how many indices can be possible in order to find out the maximum element. So the maximum element will be present at the leaf node, and the number of leaf nodes will be 105 by 2, and you will need to take the ceiling, which will be equivalent to 53. So there are 53 potential indices where your maximum element can be stored. So this is going to be the right option. And then we move over. So this is also almost the same thing. So H is a binary mean heap. It consists of n elements which is implemented as an array. So what is the worst case time complexity of an optimal algorithm to find the maximum element in H? So it is a mean heap, and you are to find the maximum element in that mean heap. So since there is, so this actually falls in this particular case. So properties, and you will need to just remember how the complexity thing works. So you will need to make a comparison of the elements in the leaf level in order to find out the maximum element. So there are n by 2 this ceiling function number of elements in your heap, and the number of comparisons will be this minus 1. Now when you are trying to find the theta of this, if you remember in data structure, when we are finding the runtime complexity, if there is anything like divided by 2 or plus 1 minus 1, so we actually ignore these what should I say, constant additions or subtractions or divisions. So in this case, this will be equivalent to theta n. So theta n by 2 minus 1, we have to ignore minus 1 and 2, and so when we are trying to find the time complexity, and that to worst time complexity of the algorithm, it will be equivalent to this theta n. And then we have strange questions like this. This falls, I think, heap properties and some common sense. That is there is a complete binary mean heap which is like composed of numbers 1 to 1023, and the depth of a node in a heap is the length of the path from root of the heap to that node. Now the root is at depth 0. The maximum depth at which integer 9 can appear is dash. So first of all, if you go through the properties, the maximum of the number of elements will be present in this case, since this is a mean heap, will be present at the leaf level, and the minimum will be present at the root level. Other than that, every element can be present in any particular order. It does not really matter. So if you apply your common sense, like 9 can be the child of 8, that is after 8, 9, and there are just all the elements are distinct, so 9 cannot have any parent after 8. Like 10 can't be a child of 9, or 11 can't be a child of 9. Similarly, for 8, the maximum element which can be the parent of 8 can be 7. And if you go by this logic, so 1 is present at the root level. So 2 will be a child of 1. 3 can be a child of 2. 4 can be the child of 3. 5 can be the child of 4. 6 can be the child of 5. 7 can be the child of 6. 8 can be the child of 7. And finally, this is the last level at which 9 can be present. Like 9 can't go anywhere beyond this level. So if you start from this level, this is a 0, 1, 2, 3, 4, 5, 6, 7, and 8. So 0, 1, 2, 3, 4, 5, 6, 7, and 8. So this is the maximum level at which 9 can appear is 8. And even if you go through this, 1 or 2 2, 1 or 2 1, no, these cannot be. 9 just can't go too far. 9 has to be the maximum element who can be the parent of 9 is 8. So this is how this kind of questions are actually tackled. And now we move on to the last question. So the number of possible mean heaps containing each value from this set 1, 2, 3, 4, 5, 6, 7 exactly once is. So this also contains the essence of permutation combination, right? So there are 7 elements in your heap. So the heap will look like this. Now let us find out how these nodes can be arranged. So 1 being this is a mean heap. So 1 being the minimum of the set will always be present at this position. And the next largest element is, the second minimum element in this particular set is 2. So 2 can be a parent, 2 can be the children of 1, and 2 can be present at either this position or this position. So let us fix 2 at this position. Now we have 3, 4, 5, 6, and 7. So for this particular position, for the children of 2, we can choose any one of these 5 elements. So there are 5 elements to be chosen from at this position, and when we take one of these 5 elements, there are 4 elements left, and we can just place 4 elements for this position. Now we move over to this particular subtree. Now when we fix the values of the 2 children of 2, we are left with exactly 3 elements. And at this position, the maximum of those 3 will be fixed. So there is potentially only one way of selecting the value for this position among the 3 remaining elements present. And for these 2, there are 2 options that can be you can just you can just select from any of the 2 elements for these 2 positions. So for this particular tree, so the number of ways in which you can actually choose is 4 into 5 into 2 ways. These elements can be this tree can be arranged. So there are 40 ways in which the tree can be arranged. And this is when we fix the position of 2 at this node. Now, similarly, if we fix the position of 2 at this particular node, there will be 40 more ways of arranging the remaining 5 nodes. So, there are 40 plus 40, that is 80 ways of arranging this particular values as a mean heap. So this is going to be the right option. Now, just since there are different ways in which binary heap, or like rather heap property questions can come in, this is, you might go through this or you might not go through this, is not that important, but I just am mentioning it. So suppose instead of binary heap, they say that this is a ternary heap. Ternary means 3. Or like there are heap where each node contains 4 children, and like that. If they ask you questions something like that, so just remember this part, and this is for indexing, when indexing of the array implementation starts from 0. For a parent node at index I, the first child will be present at index n into I plus 1. The second child will be present at index n into I plus 2. And finally, the nth child, that is just, it can be 3, it can be 4, it can be whatever. The nth child will be present at index n into I plus n. So for questions, if at all it comes for an in-array heap, it won't be a very complicated question. So I think if you just remember this part, this will be enough. So probably they'll ask you to create the heap, or how the heap is going to look like, what are going to be the first 4, 5, 6 elements, and so on. So this is all about binary heap, and if you have made this far, I really thank you for watching the video, and have a good day.